Welcome to the Ontario High School video podcast series. We're in Chemistry 1, Unit 9. This is the third podcast that deals with the historical development of atomic theory, and Learning Standards 9-5 through 9-8 are going to be discussed in this podcast. So here we go. First learning standard that we're going to go after is one that you should be very familiar with from previous classes. But 9-5 says simply this: I can identify the three major particles that make up the atom, including their charge, positive, negative, or neutral, their masses, and their relative location within the atom. I would recommend that you reproduce this table in your notes and then refer to the table as we talk about each of these. So if you'll go ahead and pause the podcast and then resume when you have this written down, we'll talk about these. Great, welcome back. The first particle we want to talk about is the electron. It has a charge of -1. If you remember from Thomson's cathode ray tube experiments, what were first thought of as cathode rays turned out to be streams of negatively charged particles that we call electrons. And the actual charge, if you take physics at some point or an advanced chemistry class, will identify this charge in terms of its actual electrical charge, which is -1.602 times 10 to the -19th coulombs. For our purposes, just declaring it to be 1 negative is sufficient. The mass in grams of an electron is very, very small, almost beyond description small, but it's 9.1093 times 10 to the -28th grams. That is a difficult number to work with, so chemists tend to use what's called an atomic mass unit, and an atomic mass unit is 1.66 times 10 to the -24th grams. And so in terms of atomic mass units, the electron is 5.486 times 10 to the -4th atomic mass units, and its location is outside the nucleus. It's in that empty space that makes up 99.9% of the atom. Okay? The proton has a 1 positive charge, and in terms of coulombs, it's plus 1.602 times 10 to the -19th coulombs. The same amount in terms of magnitude of charge, but opposite charge of the electron. Its mass in grams is 1.6726 times 10 to the -24th grams, and in atomic mass units, that is 1.0073 atomic mass units. And its location in the atom, the proton, is found in the nucleus. The neutron is a neutral particle, has no charge. Its mass in grams is 1.6749 times 10 to the -24th grams, or 1.0087 atomic mass units. Very close in mass to that of the neutron, or excuse me, to the mass of the proton. And the neutron is also found in the nucleus. In terms of a relative mass, we want to look at the proton, neutron, electron. Essentially, the proton and neutron are so very close in mass, and the masses are so tiny that we just assign them a relative mass of 1 to 1. They're actually, the proton is about 1,836 times more massive than the electron. So when we do the relative mass here, we'll say that the proton has a relative mass of 1, the neutron has a relative mass of 1, and the electron has a relative mass of essentially 1/2000th of that of a proton or neutron. Learning Standard 9-6 says this: I can assign values to the atomic number, which is represented by the letter Z, and the mass number, which is represented by the letter A, based on the number of protons and neutrons in the nucleus, and use terminology for nuclear particles appropriately, and terminology using words such as isotope, nucleon, and nuclide. Let's look at the atomic number. The atomic number, or uppercase Z, is the number of protons and is part of the information displayed on the periodic table. The atomic number is unique to that element. It determines the element's identity. the number of neutrons can vary. And when you have an element that has atoms with the same number of protons but different number of neutrons, those are called isotopes. That prefix iso means the same in Greek, and so the number of neutrons can vary, and the number of electrons can vary when the atoms form cations or anions, which are positively or negatively charged ions. But the number of protons for a particular element is always the same. A neutral atom always contains the same number of electrons as protons. But all atoms of carbon, regardless of the isotope, have 6 protons. All atoms of hydrogen, regardless of the isotope, have 1 proton. So the number of protons is unique to that atom. The number of neutrons and number of electrons can vary depending on whether it's a different isotope of the same atom or whether the element has formed an ion. Let's take a look at how information is displayed on the periodic table. This is for the element zinc, and you can see that zinc has a chemical symbol of capital Z, lowercase n. And the mass number, this is very important, the mass number, which is represented by the uppercase A, is not shown on the periodic table, but the atomic number, represented by Z, which is the number of protons, is shown on the periodic table. So you see above the chemical symbol here that round number 30, and the number of protons is always a round number. So that 30 represents the number of protons in the nucleus of all zinc atoms, regardless of the isotope. Now, down below the element's name, zinc, you see a decimal number, 65.41, and that number doesn't have a unit applied to it, but that 65.41 is the average atomic mass in atomic mass units or in grams, depending on the quantity that you're looking at. It is not the mass number, A, which is the sum of the protons and neutrons in the nucleus. The mass number of a particular isotope will always be a round number because it's simply the sum of the number of protons and the number of neutrons. And you can't have a partial proton or partial neutron, so those will always be round numbers. Let's talk about isotopes. Isotopes have the same atomic number, Z, which means they are the same element when you have the same number of protons, which is the atomic number, but different mass numbers, A. The number of neutrons in a particular isotope can be determined by subtracting the atomic number Z from the mass number A. So the number of neutrons is equal to A minus Z. Again, it is important to note you cannot find the value for A on the periodic table. The mass number is not on the periodic table. The average atomic mass is, but the average atomic mass is the weighted average of all naturally occurring isotopes. The mass number either has to be given to you or found in some other way than on the periodic table. The number of protons, the atomic number, Z, that is always on the periodic table, and you can find the value for Z or the number of protons simply by referring to your periodic table. Now we want to add a new term into your vocabulary. The mass number, again represented by the uppercase letter A, is the total number of nucleons. Now nucleons are protons and neutrons. So if I say what's the total number of nucleons in this atom, you would simply find the mass number, which is by adding the number of protons and the number of neutrons together. So both protons and neutrons are nucleons. The nucleus of a particular isotope is referred to as a nuclide. Okay, so another new term. A nucleon is a proton or a neutron that is in a nucleus. An isotope's particular nucleus, the characteristics of that nucleus, are referred to as a nuclide. For example, the nuclide of a carbon-12 isotope contains 6 protons and 6 neutrons, a total of 12 nucleons. These are terms that can be confusing because they sound alike, and you'll want to get them straight in your mind before we go on. Continuing on with the use of these terms, the carbon-14 nuclide contains 14 nucleons, 6 protons, and 8 neutrons. The mass number, A, is always a whole number. It is not the same as the average atomic mass displayed on the periodic table. The average atomic mass of an element is the weighted average of all naturally occurring isotopes of a particular element, and we'll learn how to calculate that before the podcast is done. It is important to be able to distinguish between the isotopes of the same element. So, Learning Standard 9-7 simply says this: I can distinguish between isotopes of the same element. One way I do that is Z is the same, A varies, and can identify the characteristics of the nucleus of different isotopes by the notation, as well as write the notation of different isotopes in both a long form, a verbal, and a short form, symbolic. So that's where we're headed next. We want to look at the isotopes of hydrogen, and what I would recommend that you do is to pause the podcast momentarily while you reproduce this table in your notes, and then we'll move on here. Great. We want to talk about the name, a verbal representation, and a symbol for isotopes. And in terms of the name, there are not that many isotopes that you need to worry about in terms of their names, but for hydrogen, there's some speciality here. And so the first isotope of hydrogen we're going to talk about is protium. And in protium, Z, the atomic number, is equal to 1. It has 1 proton. And A, the mass number, is equal to 1 because it has 0 neutrons. So when you add the protons and neutrons together, you get a mass number of 1. And we can represent this as hydrogen 1 with hydrogen spelled out, and then the dash 1 representing the mass number, or just H-1. That's also an acceptable verbal representation of the hydrogen 1 isotope. The symbol, though, is going to be more useful to us, and you'll see this more commonly in certain contexts. So in the symbol, what we do is the X represents the element symbol, in this case H. A is put as a superscript to the left of the symbol, and Z, the atomic number, is a subscript to the left of the symbol. So for protium, the value of A is 1, the value of Z is 1, and then you have the elemental symbol H, so it's simply 1,1H. The hydrogen 2 isotope is known as deuterium, and you may have heard of deuterium historically in terms of the production of heavy water, water H2O that contains the deuterium isotope of hydrogen is very useful in nuclear reactions, and so historically it was very prized. In fact, the Germans invaded Norway because of the presence of what they called heavy water, which was deuterium isotope water in the northern part of Norway. So this is Z equals 1 and A equals 2 because there's 1 proton and 1 neutron. Add those together and you get 2. So hydrogen 2 or H2, and then the symbol 2,1 hydrogen. Tritium is the third isotope of hydrogen, and again you sometimes hear the word tritium when they're talking about doing fusion reactions, experiments with fusion. And so again, we name these because they're very specific. It's not something in terms of a test that you would need to know, the protium, deuterium, or tritium. But they're names you should be familiar with because you'll see them in popular literature and the news. Tritium, Z equals 1 and A equals 3. There are 1 proton and 2 neutrons, so you'll notice that isotopes of hydrogen always have the same atomic number, 1 in this case, but there can be different numbers of neutrons, which then gives them a different mass. So the symbol for tritium is 3,1H. We spoke before of the average atomic mass, which you find on the periodic table. It is almost always a decimal number. There are a few elements that have a fairly round number average atomic mass, but generally They're a decimal number. And Learning Standard 9-8 says this: I can calculate the average atomic mass of an element using information provided that gives the mass of the naturally occurring isotopes with their percent of occurrence in nature. So we'll start doing a problem with this, and you'll see how that value is arrived at. We're going to do a problem together where we're going to find the average atomic mass of oxygen using its three naturally occurring isotopes. There's oxygen 16, oxygen 17, and oxygen 18. And we have the mass of the individual isotope in atomic mass units. So for oxygen 16, it's 15.9949 atomic mass units. Oxygen 17 is 16.9991 atomic mass units. And oxygen 18 is 17.9992 atomic mass units. We see the symbol for the three isotopes. And then the percent occurrence. And you'll notice that oxygen 16 is 99.757% of oxygen atoms are oxygen 16. 0.038% of oxygen atoms are oxygen 17. And 0.205% of oxygen atoms are oxygen 18. And we're going to use this percent occurrence and the mass of the individual isotopes to find the average atomic mass. Down at the bottom of the slide, you'll see step 1, which is to convert the percent value to a decimal value. And we do that by dividing the percent by 100. So our 99.757% divided by 100 gives us a decimal value of 0.99757. Our 0.038% divided by 100 gives us a decimal value of 0.00038. And our 0.205% divided by 100 gives us a decimal value of 0.00205. One of the things you'll notice is we just essentially, by dividing by 100, we're moving the decimal place 2 places to the left. At any time in these podcasts, I hope you felt the freedom to pause, to rewind if necessary. But if you need to pause to write these tables down to help you as we do these, please do that. The podcasts are designed for you to go at your own pace, so please do. Step 2, which is at the bottom of the slide, says to multiply the decimal value of each isotope by the isotope mass, and so that's what we're going to do. For our oxygen 16, we take our 0.99757 times its isotope mass, its atomic mass in AMU, 15.9949 AMU, and we get 15.9560 AMU. For oxygen 17, 0.00038 times 16.9991 AMU gives us 0.0064596 AMU, and for oxygen 18, 0.00205 times its mass of 17.9992 AMU gives us 0.036898 AMU. Our third step, again look at the bottom of the slide for the step, is to add the products of the decimal value times the isotope mass together. This is the average atomic mass of oxygen based on the weighted average of all naturally occurring isotopes. Now the chart will look the same to you as on the previous page, but up above the chart I have taken the products of the decimal value times the isotope mass and added them together. So our 15.9560 plus 0.0064596 plus 0.036898 AMU gives us a total of 15.994 atomic mass units as our average atomic mass of oxygen. Another representation of the sum of these products of the decimal value times the isotope mass added together, this is called a weighted average. We got 15.9994 atomic mass units, and if you look on a typical periodic table, the average atomic mass of O, or oxygen, on the periodic table is 15.999. No unit is given with this number for the following reason. One oxygen atom has an average atomic mass of 15.999 atomic mass units. 1 mole of oxygen atoms, which is 6.02 times 10 to the 23rd oxygen atoms, and this is a quantity we'll talk about later in the course, has an average atomic mass of 15.999 grams. The unit applied depends on the number of oxygen atoms examined. And we'll talk about that more later. Don't let that confuse you. It will actually simplify life for us down the road. We've come to the end of the podcast 3 for Unit 9 of Chemistry 1 here at Ontario High School. I want to leave you with a short thought from the contemporary novelist Mark Halperin. Well-timed silence is the most commanding expression. I wish you well.